Welcome back. In today's video, we are going to try to write pseudocode for the quicksort algorithm and understand its recursion tree in detail. Before starting, I would suggest you to watch the previous part of this video for better understanding. So let's dive into the topic. We have an array of size 7, indexing from 0 to 6, and variable p and q are pointing to the starting index and ending index of the array, respectively. After applying partition algorithm on it, which we have already applied in previous video, element 4 comes to the correct index, which was 2 here. Here we have to initialize a variable named q, which will store the correct index of that pivoted element. Now for sorting, we will make a function named quicksort, which will take array A, starting index and ending index of array A, as an argument in it. We will run our code only when the starting index of the array is smaller than the ending index. Now, as we know that partition algorithm returns that index where the pivoted element has been placed, so we are going to store that index in variable named q. Here, the starting index and ending index will be checked. After checking, partition algorithm will be performed for the indexes 0 to 6. This will return the index 2 in this scenario. Now we will apply the quicksort algorithm for the array, which is on the left side of the pivoted element, indexing from 0 to q minus 1. Now the values of q, p, and r changes to 2, 0, and 1 respectively. Again, the starting and ending indexes will be checked. After checking, partition algorithm will be performed for the same array, indexing from 0 to 1. Here we can also verify that if the pivoted element is at correct position or not. This will return index 1, which is the correct index where the pivoted element has been placed to the variable q. And again, quicksort algorithm will be performed until the base condition is not false. If it becomes false, the execution for the array, which is on the right side of the pivoted element, will be executed. So now, let's take a look at the recursion tree for this algorithm. At first, the function quicksort, indexing from 0 to 6, will be pushed into the stack, and the partition algorithm will be performed for this array. After getting the index of that pivoted element, execution for the left side of the array from pivoted element will be performed, starting from index 0 to 1. Then, the execution for right side of the array will be performed from indexes 3 to 6. Since this is a DAC, so we will divide our problem and apply partition algorithm on leftover indexes. Here division is automatically done by partition algorithm. For first left array, partition algorithm will be performed for the indexes 0 to 1. After execution, quicksort for array, indexing from 0 to 0 will execute. Here we can see that the condition of starting index and ending index is not fulfilled, so we will do nothing. And for the right array, we will also not do anything. So in execution of first left part of the array, we sorted element indexing from 0 to 1. Now in the same way, execution of right part of the array will be performed. After execution of the right part of the array, we have sorted out the elements, indexing from 3 to 6, using partition algorithm. Now at last, the control will be given back to the first call we made, and then to the user as a sorted out array. In this way, the partition algorithm is used again and again with the help of DAC, which is resulting in sorting out the full array. In next part for this video, we are going to calculate the running time complexities for this algorithm in depth. Till then, keep grinding.